So welcome to the fourth topic, which is energy and work. So energy and work are the fundamental requirements of any society, or any civilized society. So our society revolves around, and has always revolved around, acquiring energy and using energy. And in fact, the availability and the efficient use of energy is one of the limits of civilization. So in this topic, we will be looking at energy and its counterpart, which is work. We will be looking at, in particular, kinetic energy, potential energy, and work, and the relationship between each of them. And we'll start by looking at the kinetic energy and work. So kinetic energy is, somewhat unsurprisingly, the energy associated with kinetics. So that is the energy associated with the motion of an object. If an object has no motion, so if an object has zero velocity or zero speed, then that object has no kinetic energy. The formula for kinetic energy is given by half mv squared, and so the units are therefore kilograms times meters squared per second squared, or more easily and more commonly known as the joule. And the joule is named after a man called James Prescott Joule, who, among his other work, was instrumental in developing our current understanding of energy and of heat and motion. So he essentially laid the foundation for the conservation of energy principle, which is one of the fundamental principles of physics. So we'll hear a bit more about him later. And I mention this because this was only done, he only came up with this formula in 1850. And I find it quite fascinating. So these things that we take, or I at least take as obvious and for granted, so things I've known as true my whole life, someone had to figure them out at some point. And it really wasn't until quite recently that these things became common knowledge. So the kinetic energy of an object depends on the mass of the object and the speed. So as I said, a stationary object can have no kinetic energy. So if we look at a bowling ball as an example, we say the bowling ball weighs 5 kilograms and is travelling at 5 meters per second. The kinetic energy of the bowling ball is then half times 5 kilos times 5 meters per second, all squared, which is approximately 63 joules. And we know that bowling balls in general are not inclined to move. They obey Newton's first law, and therefore they should remain stationary unless they're acted upon by a force. So for our bowling ball to get up to a speed of 5 meters per second, we must have acted on it with a force. And we say we must have done work on the bowling ball. So in a physical sense, when a physicist is referring to work, he is, or she is, once again referring to a very specific quantity. So we're not referring in this case to paperwork or homework or things like this. Work in physics refers to the transfer of energy between objects. So if work is done on an object or on a particle, we say that positive work is done. So that means that energy has been transferred to the particle. So in the case of our bowling ball, when our bowling ball has been accelerated to 5 meters per second, then we have transferred energy to the bowling ball, so work has been done on it. On the opposite case, so for example, when the bowling ball hits the pins and slows down, we say work has been done by the particle. So energy has been transferred from the particle, in this case from the bowling ball, to the bowling pins, and we say this is negative work. So we know there must be a relationship between work and kinetic energy. So if we transfer energy to an object and that object changes its velocity, then we change the amount of kinetic energy that object has. And we know that since we have changed that velocity, we must have accelerated our object. And by Newton, we know that we must have then applied a force to the object. So by Newton, we know that our force is equal to the mass times the acceleration. And by our laws of motion, we know that we can write the acceleration under a constant acceleration as v squared minus u squared on 2s. So we're looking for an expression that gives us the change in the kinetic energy, or the transfer of our energy. And if we just combine these two equations here, we can see that we can get, if we multiply the force by our displacement of our object, we get our change in kinetic energy. So our final kinetic energy, half mv squared, minus the initial kinetic energy, which is half mu squared. And this formula, the force times the displacement, is our work. So our change in our kinetic energy is our transfer of energy. is our work, and that's given to us by force times displacement under the action of a constant force, because both our initial equations we use assume a constant acceleration. So we can also see, as a final note, that both the force and the displacement are vector quantities. So in this case, Fs is actually the dot product F dot S, which means that we can also write, we can do the standard trick with vectors and divide them into each individual dimension. We have our x direction, the force in the x direction times the displacement in the x direction, and so on. And in the next few videos, I'll go through examples of how to calculate the work done by a constant force and the work done by a variable force.